This talk is about software architecture versus code. And it's really been inspired by this sort of question, or this sort of statement. The architecture diagrams don't match the code. Who's experienced this? Yeah, it's a real pain, isn't it? It kind of begs the question, what on earth are you doing with these architecture diagrams if they don't reflect reality? I live in Jersey in the Channel Islands, which is this tiny little pixel you probably can't see on the screen. If this was interactive, we could pinch to zoom in, and it gets a bit bigger. Still a little bit small, we could pinch to zoom in once again, and there's Jersey. It's a small island, 9 miles by 5. Why do I live there? It's a nice place. Right, that's basically why I live there. Over the past few years, I've been kind of jetting around the world and really helping teams understand what software architecture is all about. And this is from a number of different perspectives. It's from the perspective of technical leadership and the whole balance with agility thing, and also communication. And I think architecture needs to be much more accessible to us as software developers. Sure, there are lots and lots of books out there, but lots of those books tend to address architecture from a very academic perspective. And when I was moving into my first architecture roles, I didn't really understand how those books related or mapped to my day-to-day role. So how do I fix the problem? I just write some more books. That seems the obvious solution here. This one on the left, Software Architecture Developers, is my kind of full architecture book. And the one on the right is new. It's about visualization and communication through diagrams. This one is free, so you can go and download this one later if you like to. I'm also building a diagramming product called Structurizer. And it's a way to stop people using Visio to draw architecture pictures. It's a software architecture diagram as a service thing. But I need to work on a better acronym because it's SADAS. It's not, yeah, it doesn't work very well, does it? I still do write code, and that's important because the thing I'm specifically interested in here is the intersection between the architecture world and the code world. And these are often seen as two very different, separate disciplines, but really they're just two sides of the same coin. So let's look at the tension between software architecture and code, first of all. And I'm going to come at this from the perspective of how do we communicate a software architecture? So how do we share ideas around design and intent and that sort of thing? So picture the scene. Imagine you inherit an existing code base. And let's say it's in Java, and let's say it's 2 million lines of legacy Java code. And somebody asks you to draw some pictures to visualize that system. How do you do that? Let's imagine your 2 million lines of code is actually 100,000 classes. Do you get a huge piece of paper and draw a class diagram with all of those 100,000 classes on? No. It's a ridiculously stupid idea because it would just take too long and it's just so boring, so tedious. So rather than drawing 100,000 small classes, what we do is we clump stuff together. Modules, components, services, layers. And it's those things that we draw in these diagrams. And really these things are abstractions. And abstraction is a way to reduce the amount of detail we have to comprehend. And abstractions let us reason about big or complex software systems. So rather than remembering that there are 100,000 small classes, we instead remember that there are 20 bigger things. And this is what we draw in our pictures. And when it comes to pictures and describing architecture, there are lots and lots of different ways we can do this. There's something called the 4+1 software architecture model by a guy called Philip Crichton. He basically says in his paper, to describe a software architecture, we use a model composed of multiple views or perspectives. This is Philip Crichton's model. Essentially, he says, imagine you have your software system. To describe it, you have a logical view, which is modules and components and that sort of thing. You have a development view, which is targeted at us as software developers. There's a process view that talks about concurrency, for example. And there's a physical view that talks about deployment aspects. And all of these things are kind of wrapped and pulled together by a set of scenarios or use cases. This isn't the only way we can describe software architecture. There are lots of other view catalogs, these things are called. And the thing you'll notice if you start doing a bit of investigation around them is that the names of the views varies a lot. Sometimes a logical view would be called a logical view. Sometimes it's called a conceptual view. Sometimes the development view is called the implementation view. But for some people, implementation is not about development. It's about rolling out a system to a live environment. For those of you who are no longer using physical infrastructure, should you describe your deployment using a physical view? Does that make sense? So all of the naming of these things is kind of weird. The thing you will find is this. So the logical view of a system is often very separate to the development view of the system. So the architecture and the code are kept as these two different things. And this really makes my head hurt. So if somebody asks you to go draw some pictures of your system, you've got to take all of this stuff into account. And it's like, oh, where do I start? The other option is just to cheat. Right? So if someone asks you to go draw some software architecture diagrams, you just go to Google and ask Google what it thinks a picture looks like. And if you do that, you get stuff like this. Page after page after page of very pretty, colorful block pictures. And ultimately, we get stuff that looks like this. Have you seen these sorts of things before? In your organizations, on your wikis, in your software architecture documents? Yeah, me too. You might be wondering, well, where's UML in all of this story? And UML doesn't matter anymore. So I've anecdotally amassed evidence to say that basically nobody's using it. So I've traveled all around the world, and I ask teams, do you use UML as part of your regular work? And most of them say no. And there are a bunch of reasons for that. So let's backtrack slightly. What is it we are trying to do with these pictures? If we're drawing pictures during an upfront design exercise, this is really the question that we're trying to answer. So here's a picture to describe a system. Is this what we think we want to build? If we're retrospectively drawing diagrams from an existing code base, the question is this. Right, is this really a reflective view of what we have? I think, as an industry, we lack a shared common vocabulary for describing software. So yeah, sure, we have UML, and we use terms like module and component and service, but there's no standardized definition of these terms. If we were to do a quick straw poll, you'd all have a different view of what a component is, for example. And I think this is the nut we need to crack. So forget all the notational stuff, let's get the abstractions sorted out first. Why did I do my silly zoom-in thing at the start? If you go onto Google Maps and you do a search for Jersey, you tend to get this bottom view by default. So Google Maps will zoom straight into Jersey. That's great if you want to know what the place names in Jersey are and where the various interesting things are. If you've never heard of Jersey, it's useless. So the first thing you do is you pinch to zoom out to get some context. I think we need to create a set of diagrams that are effectively maps for our software systems as well. So sometimes as developers, we want the low-level zoomed-in view of the world, and at other times we need to kind of back off and zoom out, depending on the audience that we're describing our system to. Maps are interesting. If we were to go and get two maps of Swansea and lay them out side by side, they'll both show the same things. Roads, rivers, the beaches, town centre, whatever. But they might use differing notations, different colour lines and line styles and icons and things like this. So maps are a great example of a common set of abstractions with a differing and self-describing notation. And I think that's the approach that we should start taking. So this is very much a kind of abstraction-led approach with a notation that evolves on its own. So this begs the question, well, what are these abstractions? How do we think about a software system? And this is the way that I think about it. Very simply, a software system for me is made up of a bunch of containers. A container is just an execution context. It's something that you can that you could run code inside. It's also something that you could store data inside of, for example. In real terms, it's a web app, a mobile app, a standalone application, a database, a file system. My containers are made up of components. All I mean by component is a related bunch of functionality behind a nice clean interface. And because I mostly deal with Java, my components are made up of classes. And that's it. It's just a really, really simple tree structure to describe the static structure of a software system. If you're using functional languages, maybe your components are made up of a bunch of functions. Maybe your component is a module in F#, for example. If you're dealing with database technologies, maybe your classes are actually tables, views, stored procedures, functions. So these are your lowest level building blocks. What this does is it basically puts the static structure, the static model, at the heart of everything we do. And once you understand the static structure of a software system, you can weave in all the other stuff around it. So for example, you could create a deployment model that describes how you map your containers, your web apps, your mobile apps, your standalone apps onto infrastructure, for example. Now, why have I done this? I've done it because actually I think that we as software developers are the most important stakeholders of software architecture. So this is kind of bringing software architecture squarely back into our backyard, which is ultimately where it belongs. Now we have these abstractions, we can draw diagrams very, very simply at each of them in turn. So I'll give you a set of quick examples. In Jersey, I created a website called techtribes.je. It's a really super simple content aggregator for the local tech community. And this diagram is a context diagram that shows my tech tribes system and how it fits into the rest of the world. So at the top we have various types of users, all using the system in different ways. And at the bottom we have the system dependency, so the things that my system depends on for it to work properly. So we're pulling information from Twitter, we're pulling information from GitHub, and we're pulling people's blogs in. Right, it's just a simple picture to set the scene. If this was interactive, we could pinch to zoom in on that little monkey box in the middle, and we get to see level 2, the containers. And this diagram basically says, if we open up my software system, we can see it's composed of a web application, a content updater that reaches out to the outside world and pulls all this data back, and all of that data is being stored somewhere in the middle here. So on the left, there's a MySQL database that stores most of the data. On the right, there's a MongoDB store, which stores the tweets and the blog posts that we pull in from the outside world. And there's a file system in the middle for search indexes. So it's just showing you the high-level technology elements. This doesn't tell you about availability or backups or clustering. That's the deployment view. So this is just the static structure of the system. This little thing down here, the content updater, it reaches out to Twitter, GitHub, blogs, pulls the data back. If we were to pinch to zoom into that thing, we get to see the components that live inside it. And it's the same sort of deal. So our content updater application talks to the outside world. The content updater application stores data in these things up here. And this is simply just a zoom in of the components that live inside that content updater. There's this thing here called a tweet component. And a tweet component basically lets you store and retrieve tweets into and out of a Mongo data store. So again, if this was interactive, we could pinch to zoom in on that tweet component, and we get to level 4, which is simply a class diagram of that tweet component. And this is where it all goes wrong. Who spotted the obvious problem with this method? On my previous diagram, my tweet component was a single box. When I've zoomed into the code, it's no longer a single box. It's a bunch of classes collaborating across essentially a bunch of packages. I've lost that nice abstraction. One thing on the architecture diagram is a bunch of stuff scattered around the code base. This is a really simple example. Imagine this was a big enterprise complex system. And that's really what I'm trying to get to here. So does your diagram reflect your code? The abstractions that you use to describe and think about your software, can we actually see these things in the code? And the answer is not really. So most of the teams I've visited kind of suffer from this problem. They have these nice architecture models in their head, but when you look at the code, it's something different. This is not a new problem. There's a guy called George Fairbanks who's written this book, Just Enough Software Architecture. If you're interested in software architecture, I highly recommend grabbing a copy of this. In his book, he talks about this, the model code gap. He essentially says the abstractions we use to describe software architecture, the subsystems, the components, the services, the modules, the layers, are often not reflected in the code because we're using different terminology when we're looking at the code. And really what this comes down to is a clash between how we structure our code and how we think about our code from an architecture perspective. Why does this happen? Why do we have this clash? It's very simply because, although we think about architecture in terms of components, for example, we don't have a component keyword in, say, Java. So how do we create a component in Java? We might have an interface and a bunch of implementation classes, and we might throw that across a couple of layers. There's no service keyword in Java. There's no layer keyword in Java. So when we're creating these architectural abstractions in our programming languages, we're just using combinations of interfaces, classes, packages, namespaces, for example. And the two worlds don't quite meet. So let's talk about organization of code. How do we normally do this? Well, let's imagine we're building a web application. This is one approach, the traditional horizontally layered architecture. So imagine we're following a kind of web MVC architecture. We have a layer with web controllers in, does all the user interaction stuff. We might have this middle kind of services or business logic layer, and then we might have this data layer, data access objects, repositories. Fairly common pattern? Why do we do this? We do it because that's what people tell us to do. This is a diagram I stole from a book which is an introduction to Spring. It basically says, this is how you should do your Spring web apps. A bunch of layers. You turn the page, it tells you why. Separation concerns, testability, blah, blah, blah. You download a sample code base, guess what? It's already organized into layers for you. So this is a sample code base I stole from somewhere. There's a domain package, there's a repository package, there's a service package, there's a web package. It's a layered architecture. You go on Stack Overflow, you say, how do I structure my code base? And somebody goes, oh, there's a thing you can use, and it creates a layered architecture for you. Brilliant. And from these kind of humble starting points, we build these big, complicated, layered architecture systems. Same in the .NET world, ASP.NET MVC, you download the samples, guess what? Controllers, views, blah, blah, blah. Layered architectures have benefits, and layered architectures have consequences. And when we start with this layered architecture in mind, we have these rules that say, right, the controller layer will only ever talk to the services layer, and the services layer will only talk to the data access layer. And it's this nice, strict hierarchy of stuff. So you have feature set A and feature set B, and they're really nicely built. And then you scale out the team, and somebody needs to build feature set C that needs bits of A and B. What do? You've got a whole bunch of choices here. In order to make a layered architecture work in a language like Java, if you're using a layer is a package, you have to make lots of classes public so they can be accessible from outside that package. Once you make a class public in Java, guess what? It can be called from anywhere, which is why, unfortunately, without discipline, lots of nice layered architectures turn into this horrible mess. It's funny, I do software architecture sketching workshops, and sometimes we get people's code bases, and we say, right, draw me a picture of what you think your web app looks like. And they draw this beautiful kind of layered architecture. And then we open up the code, and the arrows go the other way. I'm like, what are you doing? You might think, well, layered architectures are so passe, you know, that's 5, 10 years ago. We're now doing hexagons and clean architectures and onions. Well, that's just still a layered architecture, right? Sometimes the dependency arrows go the other way. It's still inherently a layered architecture with all of the same problems. I'm not going to say yes to this question. I don't think layers are a bad thing per se. What I do think is layers are actually not as important as we think they are. I think layers are just an implementation detail. And again, this all comes back to how we structure and think about and organize our code compared to the architecture. So I would like to see layers as simply an implementation detail of something else. Screaming architecture, blog post by Uncle Bob Martin. He basically says, if you look at building plans for a house, the building plans basically scream, this is a house. It doesn't say this is a collection of bricks and windows. It says this is a house. If you look at the plans for a library, you can see it's a library because of the things in the plans. If we open up most code bases, what do we see? Do we see it's a banking app or an insurance app? No, we see it's a layered app with a bunch of technology choices. So this is a really, really great example of someone else thinking along the same lines. Martin Fowler, last week, published this post, which is worth a read. Again, he talks about this layering thing we do. And he says layering is great. It has a bunch of nice side effects, a bunch of advantages on a small scale. And once you start getting some complexity to your systems, this whole layering thing kind of breaks down fairly quickly. And basically he says once you do get some scale, you might want to think about modularizing your code using another mechanism. And the example he cites in his blog post is this. So we switched from a horizontally layered architecture to a vertically layered architecture. So these things here are essentially your top-level domain or functional concept. Again, it goes back to that screaming architecture thing. If I look at a banking app, I want to see things at the top level that reflect this is a banking app, not it's a Spring MVC app. So that's called package by feature. So rather than having a package per layer, we're having a package per set of related things. And now our layering is simply an implementation detail of that top-level modularization. Does this solve the problem of your code becoming a mess? No, it doesn't. Because if we want to add feature set C that needs bits of A and B, what do? Same thing applies. You have to start making code public. So how do we get these two worlds to meet? Right, from an architecture perspective, I want to think of my system as being made up of a bunch of nice modules or components, and I want that to be reflected in the code. How do we do that? Well, yeah, the diagrams should show this. If I have a diagram and I have some code, the two things should match, otherwise there's no point in doing either. I'm going to come back to George Fairbanks again. He says, all you need to do is use an architecturally evident coding style to bridge this model code gap. And essentially, an architecturally evident coding style is basically dropping hints into your code base so that your code reflects your architecture. In concrete terms, this is doing stuff like throwing in annotations or attributes on key interfaces or classes. So you say, this is a component, this is a service. It might be naming conventions. So if you're building an audit component, make sure something in the code is called audit component, whether it's the implementation class or the interface. It could be a namespacing or packaging convention. So let's put all of the stuff related to the audit component in a single package or namespace or assembly or whatever. Maven modules, OSGI modules, the upcoming Java 9 Jigsaw stuff is another great way to get some modularity in the code at a high level. And also microservices. Right, so if you think about it, microservices is an architecturally evident coding style. If you draw a picture of your microservices architecture, it's a bunch of boxes with lines between them. If you look at the code, it's a bunch of separate things with collaborations between them. So how do I do this? What I do is something I call package by component. And what I really want to do here is use a packaging convention where everything related to a single component sits in a package, in a Java package. So I take my layered MVC architecture, my layered web app, and I'm going to create a package per controller or set of controllers that I think represents a component. And I'm also going to bundle the service, the business logic, and the data access layer together to create a single standalone component. What does this look like? If we go back to my tweet component example I briefly showed you, it was a layered architecture. That was how I initially implemented that particular component, and indeed all of the other components within my system. There was a tweet service interface with an implementation that delegated to a data access object with a Mongo implementation in different layers in different packages. To get to an architecturally evident coding style, what I've done is a really simple refactoring where I've taken this thing and renamed it to be tweet component, no changes. I've taken this default tweet service thing here, renamed it to something equally as horrible, I grant you, but it's package protected. So I've moved that into the same package as the interface, and I've made it package protected, which in Java means you can't see it from the outside world. I've taken this MongoDB tweet DAO and shifted it over here. Again, it's a package protected implementation detail of my tweet component. So that's kind of nice, because now what I have is a package representing my tweet component, public interface, private implementation details. Just to reiterate this so you can see it in real life, that's my package in the code loaded into my IDE. This is all the stuff related to my tweet component, and I've added my own custom annotation onto the interface. Once you add these custom annotations, you can do stuff like scan the code and extract components automatically, for example. So now what we have, if we go back to my component diagram for my content updater. Remember my tweet component that we tried to zoom into? When we do zoom into it, that's what the class diagram looks like. So now we've got a nice, really simple one-to-one mapping between stuff in the code and stuff on the architecture diagram. Our diagram is now a map that helps us navigate a code base. We can find stuff really easily. And essentially, this way of working is it's got modularity at its core. Right, so I'm trying to introduce an additional level of modularity at the code level. Now, this is not the one true way. Okay? I'm aware that this is an Agile and craftsmanship conference, and I'm aware there have been lots of talks already about testing. And some of you might have had a bit of a knee-jerk reaction to that little class diagram I showed you, related to testing. This is a little quick aside. I'm going to kind of throw it out and then run away really quickly. Did anybody see this? If you've not seen it, you should. This is a paper published by Jim Kapleen 2-3 years ago, and it basically talks about why most unit testing is wasteful. Now, it's very controversial, and there's lots of stuff I don't agree with, but there are some very good nuggets that you have to extract. And one of them is this. So if we look back 10 or 15 years ago, why did we start doing all this test doubles and mocking stuff? Well, it's because things like databases were slow. That's not the case anymore. So this thing here is a MacBook Pro Retina. It has 16 gig of RAM and a half terabyte flash disk or something. I can spin up a database, run some tests very, very quickly. So we need to be careful about some of the older practices that we just keep doing because we think that's the way we should do it. Test-induced design damage was one of the follow-up blog posts by the Rails guy. Again, controversial, but some interesting nuggets in there. And basically he says this: do not let your tests drive your design, which is kind of interesting because that's what a lot of people use tests for. And what he's getting at here is sometimes we see these big complex systems, and they're big and complex because of the testing. So in order to do lots of mocking and inserting of test doubles, we've had to introduce lots of artificial injection points. And he says that's bad. Let's go back to my code example for a second. In my layered version, the initial implementation, we've got lots of options to do testing here. So for example, if I want to test this thing in isolation to the database, what do? I plug in a mock data access object, which provides whatever I want it to provide. And that saves me writing tests against my real Mongo database. How do I do that in this new refactored world? I've removed the tweet data access object interface. Why? Because in Java you can't have non-public interfaces yet. And since my data access implementation is an implementation detail of my component, it makes no sense to make it pluggable. So I removed it. Which begs the question, how do you do unit testing? And the answer is you don't do unit testing. All of this code is open source, so you can go and find the examples. The approach I take here is basically, I don't do low-level unit testing, I do component testing instead. And what I mean by this is I create one of these, I spin up Mongo, I throw some data in, I run some tests through the public interface, and I take the data down. That works in this situation because I own the whole stack. If I didn't own the whole stack, if my tweets component was talking to the outside world, then I would have to introduce an injection point for some mocks and doubles and things. If my tweets component was doing something asynchronous, that's a bit harder to test, so I need to insert some test doubles. Right, so there's not one strategy that applies universally here. And you need to take an approach to testing based upon the things you're actually building. And that's what I want to say. I see lots of people just blindly doing very low-level testing of everything because that's what they think they should do. And I think we need to step back a bit and be a bit more pragmatic about the test strategy we use. You've seen this before? Traditional testing pyramid thing. The advice is do lots of low-level unit tests. These are nice and quick and fast running, give you fast feedback. You have a smaller number of integration tests. These are normally brittle, and break every 2 days and get ignored for some reason. Yeah? Yes. And then if you're really lucky, you get some UI functional acceptance tests on top, a small number that tests a big chunk of your system. Can anybody describe to me what a unit is? No. Because, again, we don't have this shared vocabulary. For some people, a unit is a method. For others, a unit is a class in isolation. For other people, a unit is a slice through a set of classes in terms of behavior, or a user story, or a feature. So the word unit is completely ambiguous, and we have to decide what unit means for our context. It's the same with integration. What does integration test mean? For some people, integration test integrates classes. For other people, an integration test is making our code talk to the database, for example. That's the most common form of integration test I see. But again, it's a term filled with lots of ambiguity. What can we do about this? Again, think about modularity, right? Think about that shared common vocabulary that we can use to describe our software system. And rather than that whole testing pyramid triangle thing, I think we should do something a bit different. And I think we should stop using terms like unit test and integration test. And I think we should be smarter in the terms we use. So for example, why don't we have class tests? What's a class test? It tests a class in isolation. This is where we do all that low-level fast stuff, test doubles, mocks, and so on. Why don't we have an equally large number of component tests? What's a component test? It tests a component through its public interface. For those of you who are looking at microservices architectures, you're going to need to do this from a service perspective anyway. And why don't we have some larger level system tests? So that I think there's a relationship here between the way we describe our architecture, the code, and the tests. And all of these things need to match at some point. And currently, I don't think they do. Right, so now I'm going to run away from testing. Come and grab me later if you want to talk more about testing. What's the point of all this, essentially? The point of all this is maintainability. And I'm sure you've seen highly horrible, unmaintainable systems. And the maintainability is basically inversely proportional to the number of public things you have, the number of dependencies, potentially the number of microservices. Right? The more things you have, the harder it gets to maintain. We talk about agility. A good architecture, a good code structure, gives you agility. It buys you agility. That is a quality that you need to bake into your code. And in fact, agility is a quality attribute. So when we talk about non-functional requirements like scaling and performance and availability, we need to throw agility into that pot as well. Right, so how much agility do I need from this system? If I'm working in a very slow-moving environment, I don't need much agility. We can move and evolve stuff slowly. If I'm doing the whole kind of lean startup thing, then I want lots of agility. I want to be able to push out releases and new features really, really quickly. And this all comes down to architecture again. So how do we structure our software systems? What type of software systems are we building? Well, on the one hand, we have this kind of monolithic approach, where we bundle up all of the features, all of the functionality into a single deployable unit. Every time we want to make a single line code change, we have to redeploy that whole monolithic thing. Pros and cons, it's all trade-offs. Monoliths are very easy to create. We have lots of great tooling to support that way of working. But you're trading off flexibility around deployment, for example. Also, most monolithic systems turn into that horrible big ball of mud. On the other side, we have the newfangled microservices stuff. So this is where you break your system into lots of small deployable things. You can build these things in separate languages, separate technologies, different teams around the world, have all these microservices collaborate at runtime. It's a more complex architecture. There are many more moving parts. You now have to think about service boundaries and interaction points, for example. You now have more operational complexity around deployment, monitoring, maintenance, and so on and so forth. So different styles of architectures give you different qualities. And of course, the thing I love about our industry is that we're either doing microservices or monoliths. There's nothing in the middle, except there is. Right? We can still take and blend both approaches. And an approach I'm particular an advocate for is the modular monolith. So in other words, we still have a monolithic deployment unit because it's easy to create, but we make sure it's nice and neat and modular inside. So this is why we think about nice coarse-grained components with a public interface and private implementation details. For some reason, this is a really hard thing to sell people on. People don't like this way of working. They either want to do the layered architecture in the monolith or they want to do microservices. But for me, this midground is a really nice stepping stone to microservices. Imagine your modular monolith as essentially, it's a monolithic deployment unit with lots of in-process microservices. Right? Think about it that way if you want to. If you get your boundaries right in your monolith, you can carve this thing out and make it a microservice later. So this gives you lots of flexibility without all of the baggage and overhead that a microservices architecture gives you, for example. But people still can't build structured monoliths. Right? Whenever I look at a monolithic code base, it's always a horrible mess. And that's the problem we need to fix. I see people jumping on microservices because they think it's going to fix their mess. It won't. It's going to make it worse. Because now you've got networks in the way. So we need to be able to build structured monoliths. And as I said, it's a nice stepping stone to a microservices architecture. You get lots of the benefits without going the full whole hog of the operational complexity that you get with microservices. And you need to choose microservices because microservices gives you some tangible benefits that you can't get from another style of architecture. So to wrap all this stuff up, if your software system, if your code base is hard to work with, you need to change it. Right, if your code base has evolved into that horrible big ball of mud, you need to take some steps to reverse that. Right, start thinking about how to make it more modular. Think about how you can align the way you think about your software with the code itself. So think about that model code gap and think about how you can start to bridge that by dropping hints into your code base. How? By using the architecturally evident coding style, for example. So if you have a diagram on a wall and it says there's a component in the code, make sure you can find that component in the code. This is really easy to say because I'm up here and I'm not looking at your code. The one piece of advice I can give you right now, today, is to stop using the public keyword. We get sucked into this trap of making every class public because frameworks tell us to, or it's just muscle memory. If we start using the access modifiers in our languages properly, we start to reverse this trend of our systems becoming big balls of mud. Right? You have to think about modularity. How can I force you to do this? Well, I can't. But I can incentivize you. And here's my incentive. Every time you type public class without thinking, £1 goes into a charity pot. Right, we need to get out of this habit of using the public keyword so pervasively. And once you do this, you start reintroducing modularity. And once your code starts reflecting your architecture, you can start to do some cool stuff. For those of you who hate using Visio to draw architecture diagrams, if your architecture's in your code, you can simply extract it. So that's all I have to say. Thank you very much.